Hi everyone. So you can hear me, right? Okay. So let's start. Now we were discussing about that go back end method. Let me quickly go over it. So let me just recall you that what we were discussing. So in go back end, like the whole thing is that we will be keep on sliding. So we were saying that we will be keep on sliding the window as long as we are receiving the ACKs. Once we stop receiving the ACKs or we do not receive ACK, then what we will do? We will retransmit after the timeout. Then we will retransmit the whole window, right? So that was the idea. Now let's consider 3-4 cases in go backend. Suppose that you are sending some data. So this is some case one. Let me write case one. You are sending some data. Maybe data get lost. So there could be maybe 4 cases. Data is lost, or maybe you can say that either data is lost or maybe acknowledgement is lost or data is delayed or the packet is delayed. And you can say ACK is lost or ACK is delayed. And what else you can have? Maybe you can say that anything, maybe data or ACK is corrupted, right? Is corrupted. Okay. So, okay, since we do not have much student today, should we continue? Okay, okay, we can continue. So that, like, I mean, I think students will watch it later, but yeah, we can continue. So let's just let's just consider 3-4 cases. These are the easy cases. Like if data is lost, then what you will do? If something is lost, then this receiver will say that okay, I'm expecting packet number 1. Then whenever it is receiving 2 or 3, it will just discard it and it will say, see, I'm expecting packet number 1. So it may send the ACK1. ACK1 means that I'm expecting packet number 1. I'm expecting packet number 1. Something like that. Now, at the center side, after the timeout, you will send the packet number 1. Or maybe when can like it is up to the implementation. When can you also send the packet? When you're receiving much of ACK1, which means, let's suppose I'm in the case 1 only, when data is lost, right? So suppose, so in go back and we use a cumulative acknowledgement, right? So suppose this is lost, the packet number 1 is lost, 2, 3, 2, 3, 4 you are sending, and it is receiving, the sender is receiving packet number 0. And since it is lost, it will receive this, it will receive this, it will receive this. But since this is lost, so it will not accept it, which means it will say that, okay, let me discard all of them. And then it will say that, okay, I'm expecting packet number 1, which means ACK1. I'm expecting packet number 1, which means ACK1. I'm expecting packet number 1, which means ACK1. So these ACK is cumulative, which means like you can send after every timeout also, or maybe you can send whenever you're receiving some packet, then also you can send, right? So let's suppose I'm sending after every receiving of packet, then I'm saying, okay, ACK1. So this sender, what the sender will do after timeout, it will definitely retransmit this one. But what you can do apart from the timeout, I mean, how you can optimize it? Maybe you can say if receiver is again and again asking, okay, ACK1, ACK1, ACK1 like that, then maybe before timeout also you can send it, right? The first packet, because receiver is again and again saying, so just 1 or 2 times it says maybe that it is delayed, it will get reached, something like that, right? If 1 or 2 times it says that's okay, but it is saying 3 times or 4 times, then it is like, okay, maybe I need to retransmit. Let's just retransmit before even the timeout. So it is up to the implementation. You can, for the simplicity, we can just consider that, okay, after timeout you are going to retransmit. But yes, you can, in practical sense, you can even retransmit before the timeout also, right? So in fact, in the TCP, do you remember that after 3 ACKs, we basically transfer the packet? I mean, if you have seen the TCP videos, right? In TCP, we implemented in this way. Okay. So this is the case 1 when data is lost. Let's consider another case when data is delayed. So suppose, yeah, so this is data is lost. Suppose the packet is delayed. If packet is delayed, then all other packet will not be accepted, and it will say that, okay, I'm expecting packet number 1 like that, right? But once this packet number 1 is reached, then it will say that, okay, it is done. Now I'm expecting packet number 2, something like this. So basically, Okay. So I think we have discussed this yesterday also. If packet is delayed, so let's suppose it is reaching here, so it will discard all of the packets that are out of order, and if this is delayed, and then if the acknowledgement is reached before the timeout, it will not retransmit this one. If acknowledgement is reached after the timeout, then obviously it has to retransmit. Like, I mean, after the timeout, it will anyway retransmit this one if the acknowledgement is not yet received. So basically, if acknowledgement is reached before the timeout, then it will not retransmit. It will in fact the shift the window, right? Then it will wait for 2, 3, 4 acknowledgement for 2, 3, 4, 5 like that. And then obviously, since 2, 3, 4 has been rejected, and obviously 5 will also get rejected. So that's why it has to retransmit this 2, 3, 4, 5, right? Because these have already been rejected. Similarly, if acknowledgement is delayed, then in this case, what you will do if acknowledgement is delayed, then let's suppose this acknowledgement has reached, then it is good. I mean, acknowledgement is delayed does not matter for us because it is cumulative acknowledgement, right? Is this clear to everyone? If acknowledgement is delayed, actually it won't matter much if the other acknowledgement is reaching, right? Okay. So if acknowledgement is lost, then also since it is cumulative acknowledgement, let's suppose you are sending some acknowledgement. If that acknowledgement is lost, and if some other acknowledgement is reached, then also it is okay, right? So suppose this is lost and some other acknowledgement is reached, then also it is okay. But suppose that all the acknowledgement are lost, okay? After it, all the acknowledgement are lost. Suppose then it has to retransmit the data because sender will think that okay, data is not lost, data is actually lost, right? So if all the acknowledgement are reached, none of the acknowledgement is reaching. So basically, I mean, it is just very easy. So I think let me write this is lecture 6, right? So it is very easy in the sense that you can just have some common sense. If some acknowledgement is lost, okay, let's suppose this acknowledgement is lost, but this ACK is reaching, then the sender does not worry about the earlier acknowledgement, right? So it is normal functioning. I mean, normal. If let's suppose all the acknowledgement after it is lost, if all the acknowledgement is lost, then obviously the sender has to retransmit the data. Okay, suppose all the acknowledgement are lost. This is also lost. Then sender all, let me write all acknowledgement, all ACK are lost. Then sender has to retransmit data, right? If sender is sending some data, and then let's suppose the acknowledgement for this 0, 1, 2, 3, 4. Let's suppose the window size is just 3. Okay. Suppose something like this. Let's suppose the acknowledgement for 0 has been reached. Okay. Acknowledgement for 0 is reached. It is saying ACK1, something like this. And then acknowledgement for 1, 2, 3 is not reached, which means that it is waiting for acknowledgement for 1, 2, 3. Now data is received. Okay. Data is received, but the acknowledgement is not yet come. So it will retransmit this whole window. Retransmit. If ACK for these packets has not been received, so it will retransmit the whole window. It is just a common sense. I mean, if it has not received the window, it has not received the ACK, then it will not move the window. If it is not moving the window, then after some timeout, it has to retransmit the whole window, right? Similarly, let's have one case if data is corrupted or ACK is corrupted, right? So maybe case 5, if data is corrupted, then maybe this the receiver can silently discard this data, right? Can silently discard the data, right? And it is same as data is lost. Okay. Or it may send negative acknowledgement also, or it may send negative acknowledgement. I mean, it is just optional thing. If you want, you can send it, right? So it is not compulsory, it is just optional. So similarly, if acknowledgement is lost, then the sender will think that, okay, there is something wrong maybe, like I'm not able to understand this acknowledgement. So it will say that, sorry, acknowledgement is corrupted. It is same as acknowledgement is lost, right? So let's have, like if you want, I can write case 6. If acknowledgement is corrupted, then it is same as sender will not be able to understand the acknowledgement. Basically, sender will not be able to understand acknowledgement, which is same as saying acknowledgement is lost. Sender will discard the acknowledgement. So it is like this, right? Okay. Now let's talk about a relationship between window size and sequence number. So basically it will be more clear when we talk about the selective repeat, but here also we can talk about it. So suppose the sequence numbers, right? So let's have one case. So here I want to tell you window size and sequence number. So suppose that I have a sequence numbers from 0, 1, 2, 3. Okay, available. This is ASN, means available sequence number. Which means like I will be numbering my packets something like this. So if I have to number, then I will be numbering something like this. Zero, 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, something like this, right? And then there will be a receiver. This is the receiver. Now my question is that, tell me first, can I send all of this? Okay, receiver window size is just 1. First tell me, can I send all of this data in just once? Just once. Can I send all of this data in just once? Once means that without waiting for any acknowledgement or anything. Suppose that I do have that much bandwidth, in the sense that like this 1 plus 2a that I talk about. I mean, see, basically the time in your hand is basically round trip time, right? So we have talked about it, but let me quickly tell you. Time in our hand is basically round trip time. And some people say that round trip time is just 2 into TP. Some people say it is 2 into TP plus TT, which means they also consider the transmission time in round trip time. Or if there are queuing delay or something, then you can say it is plus queuing delay or something. Plus processing delay. Right? So basically we have RTT in our hand, right? This is the time that we have in our hand. Now, I mean, you can take this as RTT, or maybe you can take this as RTT. Then it does not matter. I mean, depends on question to question. So basically, they will specify in the otherwise, like in the option, there will be just one of the option. Now, this is the time we have in our hand. In this time, how many packets we can send? We can send, let's suppose, like I mean, you can calculate it. So basically, in this time, we can send P plus TT upon TT. These many packets, number of packets we can send. Right? It is number of packets, but suppose if you want to get this is number of bytes, okay, then how you will get it? This is in terms of number of packets, like these many number of packets we can send. Suppose the same thing we want in number of bytes, then you will say RTT into bandwidth, right? This is the number of bytes you can send. And this is basically RTT upon T. So this is the number of bytes you can send. If you want to convert one to another, then I mean these are the number of bytes. Then you can divide by the length, because let's suppose 1500 bytes is just one packet. Then you can divide with this length, which is L. Then you will be getting L upon like bandwidth upon L, which is same as 1 upon TT, right? So you will be having the same formula. So basically you do have, in terms of bytes, you do have these many bytes you can send before you get the first acknowledgement, right? And these many packets you can send. So basically, in terms of bytes, you can say this. In terms of packets, you can say this. I hope that is clear to everyone, right? Okay. So that should be clear that we have like this term is this RTT is very crucial. Okay. So we can send these many packets, or maybe in this time in this RTT we can send these many packets. This is also called bandwidth delay product. Okay. Now, suppose this bandwidth delay product number of packets, let's talk about this number of packets instead of number of bytes. Let's suppose it is 100, which means like I do have sufficient time to send 100 packets. Okay. Suppose I do have sufficient time to send 100 packets, which means like like I can send if that is that I can do, then I will always do. So suppose that I can send 100 packets, but these are just I think 4, 5, 6, 7, 8, 9, 10 packets only. Okay. Suppose these are the 10 packets or whatever, but I can send 100 packets, which means that before I get the first acknowledgement, then I can send 100 packets. Okay, let me talk more about it. Like, what does this mean? Okay, maybe let me give you one picture. So basically, this is the number of packets you can send in RTT. Okay, number of packets you can send in RTT, which means you are sending something like RTT is basically this. You go here, total time, round trip time, which means total round trip time from start of the point till you get the first acknowledgement, right? So this is total RTT. Now you can have queuing delay, processing delay in the RTT. Otherwise, in generally, the RTT is basically just 2 into TP, right? Generally, this is the case. Okay. Now, uh, now let me just tell you that what does it mean that how we can send these many packets. See, like this much total time you have, right? Let's suppose this is the time. So you will be keep on sending the packets. You will be keep on sending the packets. And suppose these are the 100 packets, right? So 100 packets you can send till you get the first acknowledgement. So tell me, how many packets approximately you will be having here? How many packets you will be having in this channel? Suppose you keep on sending, keep on sending, keep on sending. The moment the first packet, okay, this is the first packet, reaches here, then what should be this number? If you can send total 100 packets, it should be 50, right? Should be 50 only. It won't be 100. Like, I mean, 100 is the total number of packets that you can send from the moment you start from here until you get the acknowledgement. So this is the first 50. This one will get reached here. Once one is acknowledged, then this ACK will start traveling, right? And then meanwhile, this ACK is traveling, you will push 50 more, right? Meanwhile, this ACK is traveling, you will push 50 more. So basically, the ACK will reach here. This ACK will be reaching here, right? This ACK of 1 will be reaching here. In that meanwhile, that in that time, you will be pushing the 50 more packets, right? So this is, let's suppose, 51. Have you understood this? So 50 packets you pushed here. The moment this one reaches here, then this ACK will also be traveling. And then the ACK reaches here. Meanwhile, you will also pushing the 50 more packets. So basically, your 100th packet is here. Your 100th packet is here. And you just received the ACK. It is like that, neck to neck, which means you just finished pushing the 100th packet and you just got the first ACK. It's something like this. Have you understood this? Okay, so you keep on sending, keep on sending, keep on sending, and the moment you finish sending your last packet, you just receive the ACK of the first packet. Okay, so like this is what it means. Like these many number of packets you can send, which means like you keep on sending, keep on sending. The moment you receive the first ACK, at that time only you just finished sending your last packet. This is the maximum number of packets you can send. Okay, now coming to this, suppose that maximum number of packets I can send is 100. Now can I send these 10 packets? These are just 10 packets. Can I send it? Let me know quickly. No. So why we cannot send it is because suppose we send it. Okay, I mean we can send 100 packets, but these are just 10 packets. But suppose we send it, then the problem is that let's suppose this 0. So there are 2 1 2 3 zeros, or similarly there are like 1 1 1 3 1, something like this, right? So suppose this 0, the first 0 you are sending here, it is getting delayed and it is reaching here, right? It is reaching here, and then meanwhile this zero that you are sending, it get reached before the first 0. So receiver has no way to identify कि this is the next zero, right? Receiver will think that this is the only zero it is expecting. So here the duplicacy, receiver will not be able to identify the duplicate packets. So that's why I should not be sending the packets with the duplicate sequence number. Because if the sequence number is repeating, then if they get interchanged, receiver has no way to identify that which one is one, which one is one, right? So here, receiver has no way to identify duplicate packet, or maybe not duplicate. I will not say duplicate. It is not duplicate. It is identify that it is next zero or the second zero, right? So that is why I cannot send all the packets like this. But let's consider another case and tell me, can I send packets something like this? Okay. Obviously, I cannot send like this, but can I send like this? Maybe let me go about it. So suppose if I ask you, okay. So suppose the sequence numbers are from 0, 1, 2, 3, 0, 1, 2, 3, 0, something like this. And then this is sender, this is receiver. Suppose if I ask you that, can we at least send, if we cannot send duplicate packets, but can we at least send these packets? I mean, if we cannot send the packets with the same sequence number, then can we send the unique packets? Is this okay? Tell me. Can we send all of this ones? Which means, can we send this 0, 1, 2, 3? Can we send like this? See, earlier case was that we cannot send this 0, 1, 2, 3, 0, 1, 2, 3. I mean, all of this. If the sequence number is repeating, then obviously we cannot send. The receiver will get confused, right? So that's never ever possible. Now let's consider this case. Can we send this 0, 1, 2, 3? The answer is still no. Reason why it is still no? Suppose the receiver size is 1. Okay, receiver window size is 1. Then what will the problem here? There is a problem that is called all ACKs are lost. Okay, so suppose that receiver is sending this 0, 1, 2, 3, sender is sending 0, 1, 2, 3, and receiver is sending ACK for 0, 1, 2, 3. Okay, ACK for 0, 1, 2, 3. I mean, the ACK number could be like increased one, which means it could be ACK1 or something like this, right? But let's suppose these are the 4 ACKs that sender is the receiver is sending. Now, suppose, okay, let's consider extreme case in this case. Suppose all of these ACK are lost. All ACK are lost. So sender will never get to know any ACK, right? And receiver will like since this 0, 1, 2, 3 has been received, like 0 has been received, so receiver will ask for 1, 1 has been received, receiver will ask for 2, 2 has been received, receiver will ask for 3, and 3 has been received. So receiver will ask for next 0, right? Receiver is asking for next 0. But sender doesn't know that this 0, 1, 2, 3 has been delivered, only ACK has been lost. Obviously, sender has no way to know this, right? So sender will think that I think that all of these packets are lost. So let me send this 0 again. Sender will send this 0 again. Now, since sender is sending this 0, 1, 2, 3 again, right? 0, 1, 2, 3 again, then receiver is also expecting 0, 1, 2, 3 again. I mean, first 0, then 1, then 2. But these are the duplicate packets. Right, duplicate packets. Receiver will not be able to identify whether these are the duplicate packets or these are the new packets. Yes, yeah, that is true. So basically, if all this is the case when all ACKs are lost, so that is the reason I cannot send even 0, 1, 2, 3. Okay, so what I can send is basically I can send 0, 1, 2. Why that is the case? See, suppose I send only this is 0, 1, 2, 3, 0, 1, 2, 3. I have this is the packet number. I can send at most 0, 1, 2. Why that is the case? Suppose in this case also, if all ACKs are lost, right? Suppose all of these 3 ACKs are lost, then you just have sent 0, 1, 2. If all of these ACKs are lost, then what the sender will do? Sender will say, that, okay, I think that all of this data is lost, then I will send this 0, 1, 2 again, 0, 1, 2 again. But what receiver is expecting? Receiver is basically here, receiver has received 0, has received 1, has received 2. Now receiver is expecting 3, right? This is what receiver is expecting. Now, since you are sending 0, 1, 2, 2 again, the receiver will say, oh, these are the duplicate, I think, right? Because I am just expecting 3. So receiver will discard it. So what I need to make sure is that whatever receiver is expecting, okay, I mean, once these packets are delivered, then whatever receiver is expecting, that should be some new set of packets that sender is sending. Basically, this window, and if these all packets, these all ACKs are get lost, then what receiver is expecting and what sender is sending, these sequence numbers should not overlap. Which means receiver should not expect neither for 0 nor for 1 nor for 2. Receiver should always expect completely new set of frames, right? So whatever I'm sending now, the receiver should be expecting like receiver. If I just think of the case, if I resend them, then receiver should not be expecting either 0, 1, 2, 1 or 2. Receiver should always be expecting something new. Okay. So we have already discussed this, but yeah. Now, now I think this go back and is completed. So this is one question. Let's just see this question. What this question is saying. So suppose you send packet number 0 and then send packet number 1, packet number 2, packet number 3. I mean, if this is your window, you will immediately send 0, 1, 2, 3. Then you receive the acknowledgement 1 or maybe acknowledgement for packet number 0. So you will shift this window and then send the packet number 4. Receive the acknowledgement 2, send this packet number 5, receive the acknowledgement 2 again, right? It means what? If you again receive the acknowledgement number 2, then it means that packet 1 has been received. So what does it mean? Then sender will say that, see, I'm expecting the packet number 2 only, right? Sorry. So basically it means that like the acknowledgement for package number 2 is basically ACK 3. Now, if we are receiving the ACK2 again, which means receiver will say that, see, I'm expecting packet number 2, I'm expecting packet number 2. It means that receiver has the sender has not received the acknowledgement for packet number 2. So if it has not received the acknowledgement for packet number 2, then the timeout will expire for packet number 2, and then it will retransmit this 2, 3, 4, 5 again, right? Okay. Yeah. So there is one very interesting question that consider that in this 1000 packets in go back n equal to 10. Suppose a scenario where the packet from the sender is lost happens 10% of the time, which means that if you are sending 100 packets, then how many packets will get lost? 10 packets will get lost. Then what is the maximum number of packets to be sent? So let's do this question. So see, in go back n, there is a problematic scenario for every lost packet, it needs to transmit up to n packet. For every lost packet, so basically in go back n, if some packet is lost, then it has to retransmit the whole window in case of packet lost. So it has to retransmit the whole window, and window size is n. So given the loss rate of 1%, the total number of extra packets that it has to send is n into 100, which is 1000. What it is saying? Yeah. So n is 10. So they are saying that loss rate is 10%. So 10,000, 10% will be how much? It will be 1000, right? So what it is saying? Total number of extra packets. Oh, okay. So the I think this is misprinting. This is not 10%. This is 1%. Okay. So this is some misprinting because here it is 1%. So it is 1% only. So which means like from this, see, like what they are saying. Let me just go to the next page. That you have total 10,000 packets, right? And then window size is 10. So they are saying that we are using go back 10, go back n, where n is 10. Now loss rate is 1%, which means that number of packets get lost is how much? 100, right? Because 10,000 into 1% will be 100. So it is 100 basically because of 1% of 10,000. Now, what we are saying, let's suppose that the 100 packets are get lost. So because of this 100 packets, right? Because of 100 packets, we will send total 1000 packets. Why? Because 100 into 10. Because for each packet, we are sending 10 packets because the window size is 10. So if some packet is lost, let's suppose you are sending 0, 1, 2, 3, 4, 5, 6, 7. Okay. Something like this. Let's suppose third number is lost. Okay. I mean, you have received for 0, 1, 2, and then this third is lost. If third is lost, then what you will do? You will retransmit the whole window. So if some packet is lost, you are going to retransmit the whole window in Go backend. So that is why for every packet, we are retransmitting the 10 packets. So for 100 packets, like we need to retransmit. If 100 packet get lost, then we do not only need to retransmit this 100 packets. In fact, we need to retransmit 1000 packets. But again, now see 10,000 we originally wanted to retransmit, but because of that 100 got lost. Out of this 100 got lost, and we ended up retransmitting 1000, right? So 1000 retransmission. Now out of this 1000, how many will get lost? 1% of that, which means 10 will get lost. It means you need to retransmit 100 retransmission. Now out of this 100, if you take the 1%, then it will be 1 will get lost. So you need to retransmit 10 retransmission, right? Out of this 10, how many will get lost? 0.1, right? So I mean, you need to this is 1%, so 0.1. I don't think then we need to add the 0.1 because that's not integer. So how many packets you are retransmitting? I mean, how many packets you are total transmitting or maybe retransmitting? Apart from this 10,000, you are retransmitting this, you are retransmitting this, you are retransmitting this. Sorry, you're retransmitting these 10 packets because of this one packet. So these many total packets you have to extra transmit apart from this 10,000, right? So let me check it, which is 1010, right? So yeah, it is 1010. These many packets you have to extra retransmit apart from this 10,000. Okay. So this is about the Go backend. Now let's solve few more questions. What this question is saying is that suppose that sender and receiver are using ARQ, automatic repeat request, to perform reliable data delivery. How many sequence number are needed to implement the stop and wait? For the stop and wait, how many sequence number you need? 1 or 2? You need 0 and 1, right? So 2 sequence numbers. Can you only work with 0? I don't think you can only work with 0. Why? Because suppose this 0 get delivered, and then if this ACK is lost, then you are like, this is new 0, right? Or maybe this 0, I mean, you will not be able to identify in many of the cases. Then if this is okay, this ACK is lost, then this is old 0, right? Old 0. But receiver will be expecting for the new 0, and receiver has no way to identify whether it is old 0 or new 0. So basically, you at least need two sequence numbers. Now, what they're saying in Go backend protocol, the window size is 6. Okay. I think, yeah. So the window size is 6. Segment with the sequence number 1, 2, 3, 4, 5 has been sent. Okay. They are starting with the sequence number 1. 1, 2, 3, 4, 5 has been sent, which means it is in the window. And window size is 6. Okay. So maybe you will say that 6 packet, 6, 7, 8, 9, 10 are waiting to be sent. Okay. The sender just received the ACK for the segment 1. So they are saying that 1, 2, 3, 4, 5 has been sent, and this 6 has not been sent, but yeah, you can definitely send it once. I mean, they have just been sent. Now your next you are going to send this 6. The sequence number is starting from 0, 1. That's the only confusion. In the Go backend protocol, the window size is 6. The segment with the sequence number 1, 2, 3, 4, 5 has been sent. The sender just received the ACK for the segment 1. The segment 6, 7, 8, 9, 10 are waiting to be sent. draw the diagram showing this scenario. So they are saying 1, 2, 3, 4, 5. Segment with the sequence number 1, 2, 3, 4, 5 has been sent. And this is actually the answer. 6, 7, 8, 9, 10 are waiting to be sent. So basically, if the window size is, first of all, if the window size is 6, then you will send all of these 6 packets, right? You will definitely send all of these 6 packets because window size is 6. So you will immediately send this 1 to 6. Now they are saying that the acknowledgement for 1 is received. In this case, what you will do? So suppose in your window, if 1, 2, 3, okay, let me go here. In your window, if 1, 2, 3, 4, 5, 6 is there, now you just receive the acknowledgement for 1. Then what you will do? You will slide the window and you will immediately send 7, right? You will immediately send 7 also. The sender just received the acknowledgement for segment number 1. Segment 6, 7, 8, 9, 10 are waiting to be sent. I don't understand that what does this mean? Okay, so I think there is some problem in this line. So what they are saying, draw the time diagram showing this scenario. So if the window size is 6 and these has been sent, the sender just received the ACK1, then you will just immediately send the 7 also. So basically the diagram could look like this, that 1 has been sent and 1 has been ACK for this has been received. And now what you are going to do, like in between, you are going to have this 2, 3, 4, 5, 6, and you do not know, maybe they have reached, maybe they have not reached. But the moment you receive the ACK1, then immediately you will send the 7 also. Okay. So this is the diagram. This 7 will come just after this ACK1, not before the ACK1. Okay, that's the catch. Now what they're saying, which segment can the sender send before it must wait for the next ACK? Yeah. So which segment can you send? Like I mean, they are saying that in the above question, which segment it can send before it waits for the next ICK? It can send the 7th one, right? I mean, 7th one we have just sent. So it will be the 7th one. Segment 7 can also be sent. Okay. Yeah. So now let's do this. Now they are saying sometime later the sender transmitted the segments 20, 21, 22, 23, 24. Okay, they do not have 25, or maybe this is also, I think, misprint. Okay, so they are saying that sometime later you are transmitting, the window size is 6, they are transmitting from 22, maybe 25 or 26. Okay, and window size is 6, so 1, 2, 3, 4, 5. I think this should be 25. Should be 25. However, the segment 22 got lost. If go back n is used, what segment would the sender have to retransmit it again? Yeah, what are the segment that you will retransmit again? Can anyone tell me? If you are sending 20 to 25 and segment 22 got lost and all of this has been received. So see here, this is 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, something like this, right? Now they are saying that you have received for, this is your window. Initially your window is from 20 to 25 and you have received for 20, 22, 20 and 21, and 22 has been lost. So maybe this will be something like this, right? The situation will be something like this. You will slide the window 2, and then since it is lost, so you will stuck here. Now what are the segment you will retransmit? From 22 to 27, you will say 22 because it has been lost, 23, 24, 25, 26, 27. So the segment that you have to retransmit is the whole window, this window, which is 22, 23 till 27, right? Now suppose the same situation as above could have occurred in selective repeat. Okay, so in the selective repeat, if something is lost, then you will retransmit that only. So we will see this little later. Okay. So now let's just move to the more questions. Suppose we have a network connecting two hosts with RTT of 100 millisecond and a bottleneck rate of 30 MB per second. So basically bandwidth is given to us, which is 30 MB per second. So bottleneck bandwidth means, like, I mean, this is same as like concept of bottle. So suppose you have a bottle and then there's a neck of the bottle, right? So if there is a neck of the border, like it doesn't matter like how much how much area or the how much surface area it has, or the how much circumstances it has, then the only thing matter is that what is the diameter of this neck, right? Because based on that only the water will flow. So that is why that's called bottleneck. I mean, what is the minimum limitation that you have? So this neck is the limitation with us. So in case of this computer network, I will be saying the bottleneck in the bandwidth means like there might be multiple connections in between, but let's suppose this is having the lowest bandwidth, then this will be the bottleneck bandwidth, right? Even though I can send at the higher rate from A to B, but there is like there is no point in sending the higher rate because B is very slow, right? B is slowing down. So basically, like if I'm sending at the higher rate, then there will be too many packets at B, and if we do not have a much larger queue, then it will be a problem for B, right? So that's why this B to C is a bottleneck. Now what they're saying is that the bandwidth is given to us, which is 30 megabits per second. Suppose that one host is trying to send a message to other, that is communication is in one direction. In this question, you will consider the effectiveness of stop and wait protocol versus the sliding window protocol. Assume that the packets are of length 1500 bytes. There is no queuing in the routers. What is the maximum throughput between these two hosts? What is the answer? Maximum throughput. Maximum throughput is always bandwidth, right? It is always bandwidth when the efficiency is 1. So basically, if you are too much efficient, maybe you do not have any other limitation because of the sequence number or any other limitation, right? Then you can send all of the packets that are required in how much time? In RTT time. Or in this time, how many packets you can send? You can send these many, like these many bytes you can send. If you want number of packets, you can divide by L. So these many packets you can send in this much time, RTT time. Bottleneck is throughput or the bandwidth? Bottleneck is bandwidth. Bottleneck is bandwidth, which means like at this rate you can at most I mean, if from A to B, let's suppose this is A, this is B, this is C, this is D, something like this, right? And this is, let's suppose, very low. Okay, this bandwidth is very low. Let's suppose 30 megabits per second. Then in this case, it doesn't matter how much at what rate you can send from A to B. B can send at very slow rate. So that's why the total bandwidth of this channel, this communication will be just this bottleneck, which is 30 MB per second. Okay, this is the maximum you can do. Okay, and now it depends on your efficiency. If you are actually doing this maximum, then your efficiency is 1, and throughput is also this bandwidth. If you are not doing that much, then throughput will be lesser than this. So this is the maximum you can do. If you are not doing that much, then throughput will be lesser than this. You cannot do greater than this. That is for sure, because that's the bottleneck. Okay, so what is the next thing? In a standard one packet stop and wait protocol, what percentage of the maximum throughput will be used? So how much throughput you are using basically? What percentage of the maximum throughput will be? So maximum throughput is bandwidth basically. I mean, they are asking about the efficiency, how much efficient you are. So how you can find out it? This is maybe 1/1 plus 2a, right? Okay. So this RTT is given to us, which is 100 millisecond. Or maybe you can say that you are like you can find out, maybe you can find out the throughput, which is basically you are saying you are sending 1500 bytes only, right? You are sending 1500 bytes, which means one packet only, 1500 bytes. In how much time? Can anyone tell me quickly? In how much time we are sending 1500 bytes? Yes, in RTT, which is 100 millisecond, right? So basically in 100 millisecond, you are sending this much, these many packets, which means 10 to the power minus 3 seconds. So it will be 15 into 10 to the power 3 bytes per second, right? 15,000 bytes per second is my, or maybe if I want to represent this in the This is in the mega, right? So which means this is 10 to the power 6. So I can say that, okay, let me just multiply by the 8 also, just to compare. 15 into 8 kbps. It is kbps, right? So it is in kbps, it is in mbps, which means, right, that this bandwidth is too high, but because of the stop and wait, my throughput is very less. So how we calculate the throughput? This much data we are sending in how much time? In this much time, right? That's my throughput. So that's how we are calculating the throughput. Now they are asking, if let me check, if they are asking in the percentage, then we can also call the also calculate the percentage. So they are saying the throughput is this, which is 1500 bytes we are sending in 100 millisecond only, right? So this is the throughput, which is this much. This is 0.4% of the maximum throughput, which means that if you find out with respect to your bandwidth, which is 30 megabits per second, and this is just 0.12 megabits per second, then if you find out the percentage, it will be 0.4%. Or maybe you can directly find out 1 upon 1 plus 2a. Okay, so you are sending one packet, and you could have sent 1 plus 2a packet, or maybe some people just use 1 upon 1 plus instead of 1 plus 2a, they just use 2a only. So let me check if my parameters are given here to find out this a. I think the propagation time and these are not given separately, right? So since these are not given separately, I think I cannot directly use this formula. Have you understood? So basically, this propagation time and transmission time are not given separately. The RTT is given directly to me. Okay, that might be having a mixture of propagation and transmission time. So RTT could be 2TP plus TT, or maybe just 2TP. I don't know. I mean, depends on the question. So basically, RTT is given directly to me. So maybe I don't think I can use this formula, right? Okay. So anyway, like this is how we can calculate the throughput. And then once we know the throughput, then we can also calculate the percentage of the throughput with respect to the bandwidth. Now let's see the last question. Now suppose we use the sliding window protocol instead of using the stop and wait, where n outstanding frames can be sent. Then what is the maximum throughput will be used? What percentage of the maximum throughput will be used? So earlier you were just sending one packet, right? Which means your throughput was 1500 bytes per 100 millisecond. Sorry, 100 millisecond. Now you are saying you can send n packets. Then what will your throughput? Your throughput will be, yes, very nice. So it is 1500 bytes into n. I mean, this will be number in terms of number of bytes upon millisecond. So basically, throughput will be just multiplied by the n. Okay. So this is earlier, if the percentage was 0.4%, then it is 0.4 into n%. I hope that is clear to everyone. So basically, the concept should be clear that throughput is just in whatever time we have in our hand, in how much time, how much data we are sending. In terms of packets, I can calculate. Like in terms of packet, I'm sending one packet. I could have sent maybe 1 plus 2 a packet. Some people just say that, okay, you could have sent only 2 a packet. Okay. This is how I can find out the efficiency. Or maybe if not in number of packets, if let's suppose if I want to find in number of bytes, then can anyone tell me what is the number of like how many bytes I can send in the meantime that I have? So what is the time I have? This is the time I have, and how many bytes I can send in this time? Into bandwidth, right? So these many bytes I can send in the RTT time. That's also called bandwidth into delay product. Okay, so now let's go to the next question. Consider the go back and selective repeat protocol. Okay, they are asking about the selective repeat also. Just a second, let me go to this question. Okay, so I will just come to that question little later. Let me go to this question. Consider the go back and protocol. Suppose the size of sequence number space, number of unique sequence numbers is n. Suppose they are saying the number of unique sequence number is n. The window size is also n. Okay. Show tracing showing so the trace showing the senders, receiver, and the message they exchange over the time. That the go back and protocol will not work in this case. So they are saying that give us a diagram where the go back and protocol will not work if the sender window size is same as the total sequence number. What is that case? Suppose that total sequence number is 0, 1, 2, 3 is available, and your sender is sending all of this at once. 0, 1, 2, 3. Okay. If you are sending all of this at once, then it will be a problem. Yeah, all ACK lost. It will be a problem when all ACKs are lost. In this case, the receiver is actually expecting packet number 0, which is new 0. Receiver is expecting new 0. But I'm sending the old 0 because all ACKs are lost. So I'm sending the old 0, which is old 0, 1, 2, right? 0, 1, 2, 3. So in this case, it will not work. Let me see the answer. See? Yeah. Or if all the ACKs are lost, then there will be a problem of duplicate, right? If all ACKs are lost. Okay. Now, what is the second question? Consider the go back protocol and suppose the base of the sender window size is X. Base of the sender window size is X. Okay. Is it possible for the sender to receive an ACK for a packet that has a smaller sequence number than X? Base of the sender window is X. Just a second. I'm not 100% sure about this terminology. Base of the sender window. Okay. So this is the answer for C. Let's just check that what is the question, what is the answer. So I think the sender window, let's suppose this is 1, 2, 3 and it is sending 1, 2, 3. Okay. And then suppose it received the acknowledgement for 2, 3, 4, something like this here. And it is retransmitting. Okay. So, okay. Let's suppose after this timeout has been occurred and it retransmit all of this packet. But this old ACKs it is receiving the old ACKs. Now it receives this new ACK also. These are the old ACKs basically. Now it receives the new ACK also. Then what is that question? Is it possible for the sender to receive an ACK for a packet that has a smaller sequence number than X? Oh, yeah. So what they're saying is that if you are starting with some number X, okay, base, I think we are starting with some number X, let's suppose 1. Okay. So if you are starting with 1 and then you are sending, let's suppose 1, 2, 3, then is this possible? I mean, currently in your window, let's suppose currently in your window is 4. Then is this possible to get an acknowledgement which is lesser than 4? That's the question. I think it is a good one. Right. So they are saying that currently whatever you have in your window, let's suppose 0, 1, 2, 3, 4, 5, 6. Okay. Suppose this 4, 5, 6 is there in your window. Or maybe you can start with 1 or 0, does not matter. So suppose that 4, 5, 6 is in your window, then you will send the 4, you will send 5, you will send 6. Now, here you are waiting for acknowledgement, right? Either for 4 or 5 or 6. Like since it is cumulative, if you receive one of them, based on that, you will slide your window. Now they are saying, can you receive an acknowledgement for maybe acknowledgement for 1, acknowledgement for 2, something like this? See, the straight thinking is saying that, okay, how can acknowledgement 1 has arrived here? Because acknowledgement 1 must have arrived only when I have shifted, So one of the idea that we can maybe think of is that maybe this ACK1 might have been delayed, right? Might have been delayed. This is also one of the possibility that ACK1 might have been delayed and it is reaching here. But in between, you might have received ACK3 directly. Right? Maybe you have received the ACK43. ACK3 means just ACK43. I mean, it should be basically ACK4, but I think you will get confused. So that's why I'm just using ACK3. Then once it receives the ACK3, immediately it will shift the whole window to 4, 5, 6. But this ACK1 is delayed. So is this possible? Then yes, it is very much possible, right? If some ACK is delayed. So maybe they can ask you as an MSQ, right? It is possible when, in which of the following situation? ACK is delayed. This is one of the following situation. Another could be that they have shown that, okay, so here they have shown that all the AC keys are delayed. Okay, so you can write AC key is delayed is one of the option. Yeah, so AC key is delayed, and this whole window is basically slided, and window has slided. So no retransmission. I mean, in this case, I'm not doing any retransmission. But suppose all AC keys are delayed, then also it is possible. Delayed. And in case of retransmission also, it is possible. Actually, it is very much possible to get some ACK because the ACK is delayed, right? And what could be the consequences of ACK delayed? Maybe you have to retransmit, maybe you may not have to retransmit. It depends that if one of the ACK has been received, then maybe you don't have to retransmit, right? If let's suppose the ACK3 is received, then you don't have to retransmit. Let's suppose but all of the ACKs are delayed, then you may have to retransmit. But yeah, this is possible when some ACK is delayed. And what could be the consequences apart from that? Like you may have to retransmit, you may not have to retransmit, right? Okay. Now let's go to the next question. So they're saying that when implements a reliable data protocol intended to provide exactly one semantic, each packet has an 8-bit increasing sequence number starting at 0. Okay, so intended to provide exactly one semantics, each packet has 8-bit incrementing sequence number starting at 0. As the connection progresses, the sender wraps around the sequence number once it reaches 255 and going back to 0. So basically, you have the sequence number starting from 0 to 255. Okay. Each packet size is as equal to 1000 bytes long. Suppose that the link capacity between sender and receiver is this much. So this is the bandwidth that they have given. Round trip time also they have given. So if bandwidth and round trip time is given, then what you can do immediately? You can find out bandwidth into delay product, which is this is milliseconds, right? This is in millisecond. So 1 megabytes into 100 into 10 power 3 10 power minus 3 seconds. So basically these many MBs. So you can find out this is mega is 10 power 6. So this is 10 power 8, 10 power 5. So 10 power 5 bytes, right? These many bytes, which is basically you can say that 0.1 megabyte. So these many bytes you can send before you receive the first acknowledgement, right? I mean, this is the maximum bytes you can send. In terms of packets also you can find out, maybe you can divide by 1000. So maybe you can divide by 1000 also. Let me divide by 1000. So if you divide by 1000, you will be getting 10 power 2 packets. 100 packets you can send. So basically you can send 100 packets before you receive any acknowledgement. Okay, so KS is asking if RTT and TT both are given, then we have to take RTT as 2 into TP. Yeah, so if RTT is basically round trip time, I mean, they will define it, right? What they mean by round trip time. So round trip time means like theoretically it means the moment you send some data, you start sending some data till you receive some acknowledgement, like this total time, this round and trip, like total round trip time. So they will define it. So if they're not defining it, I mean, if they're not saying anything, then yeah, you can take anything. Maybe you can take it 2 TP, or you can take 2 TP plus TT. I think answer should not, I mean, one of the option, there should not be two options. One is having only 2 TP, another one is having 2 TP plus TT. Actually, it is controversial in the sense that there is no fixed answer to that. Even I have checked the multiple resources. Somewhere like this is clearly written that I mean, in these questions also, like in MIT questions also, you can see that they will either specify. If they are not specifying, then they will say that you can take anything. Okay, so you can take either 2 TP only, or you can take 2 TP plus TT. the answer should not differ. Like only one of the options should match. Okay. So now you can send 100 packets before you get acknowledgement, right? So from here we can find out that we can send 100 packets, right? Okay. Now let's see the question number A. What is the highest throughput achievable if Ben's implementation is stop and wait? What is the highest throughput? It is just sending one packet. How much you could have spent? 100 packets. So this is the throughput. Sorry, this is the efficiency, not the throughput. So this is the efficiency. If you want the throughput, you can multiply by the bandwidth also, right? So this is the efficiency in the sense that these many packets you could have sent. This is just you are sending. So this is one of the way to find out the efficiency, and then you multiply by the bandwidth. You will be getting the throughput. So basically, efficient bandwidth is 1 MB per second. So basically, it is 1 into 10 to the power 6 per second, right? So it will be 10 to the power 4 mega. So 10 to the power 4 bytes per second, right? Bytes per second, which is 10 kbps. You're getting my point? So if you multiply these two, you will be getting 10 kbps. Let me check the answer. Yeah, 10 kbps. So how they found out? Okay, they are just finding out with the directly. They are saying in this much time you are sending just one packet, which is 1000 bytes. So from here you can find out. And one other way that I just used is that you are sending one packet out of, like, you could have sent 100 packet. So this is your efficiency, and then you can multiply by the bandwidth. Or maybe if this is one of the way, maybe you can directly say that you are sending how many bytes in terms of bytes. If you if you have the bytes, then I think you can directly calculate. You are sending, what is the size? 1000 bytes, right? You are sending only one packet, means 1000 bytes. And in how much time you are sending it? In RTT time, in 100 time. So basically, in term, if you have the length, then I think you can directly find out it, right? So this is how you can find out that, okay, this is the throughput. I hope you understood. Is this okay to everyone? Let me know. Okay. Now let's go to this next question. To improve the performance, Ben implements a sliding window protocol, assuming no packet loss. Okay, so he is implementing sliding window. Now in the sliding window, there are two types, either go back and or selective repeat. Now they're saying, assuming no packet loss, what should be the bench and the window size in order to saturate the link capacity? So it want to use the link capacity to the fullest. So how much packet it should send? How much packet it could send? It should send. So basically 100 packets it can send. If you want to utilize it fully, then your window size should be 100, right? You got this point? So basically 100 packets you can send. If you want to utilize fully, then your window size should be 100 only. So yeah, so if your window size is 100 packets, basically packets. Now in terms of bytes also, if you want to calculate, then you just multiply this 100 with 1000 bytes, right? So one packet length is 1000, so it will be 10 to the power 5 bytes. Okay, so this is 10 to the power 5 bytes. Or otherwise you can just find in terms of packet. So your window size should be 100 packets, because 100 packets you can send. Okay, whenever bandwidth and delay is given, then you just find out the number of packets you could have sent. Now let's do this. Ben run his protocol in increasingly higher speed bottleneck links. Okay, so suppose that Ben is running his protocol, and now the bottleneck links has been increased. Okay, should I explain it again? See, B is asking you that what should be the window size to use the fullest capacity that the network is providing you. Okay, so network is saying my bandwidth is this, my delay is this, or something like this, right? So network is saying that you could have put 100 packets on the link before you get the first acknowledgement. This is what network providing you. And if you want to use this network flashed, then what should be your window size? If you can put the 100 packets on the link before you get the first acknowledgement, then what should be your window size? It should be 100 only, right? So that's why the 100 packets should be your window size. So that's what it is saying. And now in terms of byte also you can calculate, or if you want to leave with the packets also, then it is fine. Now for this 100, like this window size should be 100. To provide this window size 100, what are the sequence number and all? This is another story. So the sequence number should be 101 at least in Go backend, right? I mean, this is another question, that what should be the sequence number, minimum sequence number and all. But yeah, window size should be 100 to get it maximum, because 100 packets I can send. Now Ben run his protocol on increasingly higher speed bottleneck links. At a certain link speed, he finds that his implementation stopped working properly. What can you explain what might be happening? What threshold link speed caused this protocol to stop working properly? So Ben is increasing the bottleneck links, and now after some certain threshold, that the protocol is not working. So let's just understand this question maybe on the next page, what they are trying to say. See, they are saying that your current bandwidth is 1 MB, right? Your current bandwidth is 1 megabytes per second. This is your current bandwidth. Now they are saying that you are increasing, and your RTT is also fixed, which is 100 milliseconds. That is why, because of this, we can put 100 packets on the link, right? Now what they are saying is that if you're increasing this bandwidth, then obviously you can put more packets on the link, right? If you're increasing the bandwidth, then you can put more packets in the link. But they're saying that after certain threshold, the protocol is not working. Then what is that threshold? Why you would think that protocol will not work? Have you understood this question clearly? Yeah. So here the maximum sequence number is also given is 255, right? I mean from 0 to 256. So sequence number bits, yeah, that's nice catch, is 8 bits. So maximum sender, basically maximum sender window size could be how much? 255 in terms of size, right? I mean from 0 to 255 packet number you have. So in one time you can send from 0 to 254, right, which is 255 in terms of size. So 255 is your size of maximum window size. Like you cannot send more than this. So you can put maximum, you can put 255 packets on the link, which means bandwidth into 100 milliseconds is equal to 255. Okay, so bandwidth, okay, like I will take care of the units. It is in millisecond. It is 255 packets. Let me convert that to bytes, which is 1000, right? 10 to the power 3 bytes. So it will be if you have bandwidth which is 255 into 10 bytes per millisecond. So since it is millisecond, let me convert this into seconds, at least into 10 to the power 3, right? So you will be having it. How much will be the bandwidth? If this is 10 to the power 3, then you will cancel this out, and then you will say this is in the seconds. Then it will be 255 upon 100. So 2.55 bytes per second. Is this correct or something is wrong? Bandwidth is bandwidth into okay, millisecond is 10 to the power minus 3. This is 10 to the power minus 3, right? So if you just do this calculation, then this whole thing will be, this is 10 to the power 3 only. then you can say it is 10 to the power minus 1, and then if it is goes here, it will be 10 to the power 4. So 255 into 10 to the power 4, so which is 2.55 into 10 to the power 6, which is megabytes. So after this bandwidth, if you have this much bandwidth, then you can put how much packets on the link. If you have 2.55 megabytes per second, with this much bandwidth, how much packets on the link you can put? You can put 255 packets on the link, right? With this much bandwidth. Now, if you increase the bandwidth, then you can put more packets, but that's not allowed, right? So I think this is the bottleneck bandwidth. Like if you have if you want to increase more bandwidth, that is not useful, right? Because the maximum limit is 255 packets. Yeah, so that's what they are saying. See here, 2.55 in megabytes per second, right? So what they're saying is that sequence number wraps around causes his protocol to stop functioning properly. So basically, if you put more than this 255 packets, which means you are putting 0, 1, 2, 4, 54, and then you are also putting this 255th number, or maybe after it, which is 0, or you are putting maybe at one time. Apart from this, let's suppose at one time, if I'm putting more than this, maybe something like this, then it will be a problem, right? It will be a problem. So you can, if this is the bandwidth, you can put maximum 255 packets. So sequence number wraparound causes his protocol to stop working. When this happens, two packets with a different content, but the same sequence number are in the flight at once. Okay. So suppose you are putting all of this, then two packets with the same sequence number, but with the different content are in the air. Are in flight means in air. So they are, they like you are just sending them, all of them. You are just sending all of them. So they are in the air. So an acknowledgement for the first spirituously acknowledge the second as well. So basically, like if this packet instead of this packet, like it, I mean, you know the whole story, right? So we have already explained this. Possibly cause the data loss in the Ben's reliable protocol. This happens when the bandwidth is 2.55 megabytes per second. So if you increase bandwidth more than that, then it is not actually useful, because your limit is 255 packets in a air. Okay. Now let's solve this question. Suppose you have a network which is saying to monitor, observe the, okay, this is also related to, I think, selective repeat. So let's just quickly do selective repeat, and then I will do this question also. Okay, so we can do this question also. I mean, we can do this question now also, or maybe after. Let me just first introduce you selective repeat. Okay, and then we will do the remaining questions. So in selective repeat, what we do, we basically have one, like the sender window size and receiver window size in such a way that receiver window size is more than one. So we can have more than one packet in a receiver window size, which means the receiver can wait for more than one packet. Okay, generally the sender window size and receiver window size are equal. So see here, in terms of acknowledgement, here the acknowledgement is cumulative, here the acknowledgement is individual. Okay, so I'm doing the individual acknowledgement. Here the window size was something like this. If m bit was available for the sequence number, then total sequence numbers are available for me is 2 power m. Then 2 power m minus 1 I will give to the sender, and 1 I will give to the receiver. Here I will divide those m sequence number in the equal parts. Okay, so I will tell you that why all of this is necessary, or maybe if you have seen the lectures, then you know this, right? That why it is necessary. Now in terms of timer, I will be having for each packet, timer for the each packet. So if I'm sending this, then timer for this will run, timer for this will run, like that. So if some packet timer got expired, then I will retransmit it. If some packet ACK has been received, so ACK are individual here. If one ACK has been received, I will mark it, okay, this has been received, this has been received. And then the moment 0 has been received, I will immediately slide it. So basically what is happening here is this. See, in case of sliding window, sorry, in case of selective repeat, what is happening? Basically, you are sending, let's suppose 0, 1, 2, 3. This is your window. And then let's suppose in your packets are like this 0, 1, 2, 3. let's suppose you are sending 0 and 1 at once. Okay, or maybe let me have little more sequence numbers. Maybe let's say this is 4 5 6 0, like that, right? So suppose this is your sequence numbers that you have at the with this protocol available. Okay, now suppose you are sending the packets which are this in this window. Let's suppose you have at one time you can have anything, but at one time let's suppose I have 0 to maybe 0 1 2. Okay, so I'm sending 0 1 and 2. Now suppose receiver is also expecting receiver window size could be anything, maybe it is also 3. Okay, so if this is sender window size 3, receiver window size let's suppose 3, which is 0 1 2, suppose. Okay, so here in this case basically like I mean you can have 6, there is no problem, but let me have the sequence number till 5 only. Like there won't be any problem even if you have 6. Okay, but just for the sake of explanation, let me just have it till 5. So sender is sending 0 1 2. Now suppose whenever this 1 is received, so 1 is receiving first, so receiver will say okay 1 has received. Now if 0 has been received later, then it will say 0 has been received. So if let's suppose 1 has been received first, so it will receive 1 and it will send the ACK. Send the ACK are individual. So the moment it send ACK, now it will say that okay, the moment it receive the ACK, it will say that okay 1 has been received. It will just tick mark it. Now tell me, will it slide its window after 1 has been received? No, right? It will not slide its window. Why? Because 0 has not been received yet. Now, the moment this is 1 has been received, the moment 0 is also received. Okay, so here the ACK numbers are the same. I mean ACK 0, ACK 1 like this, right? So for 1, the ACK is just ACK 1. For 0, the ACK is just ACK 0. So if 0 has been received, then it will say, okay, 0 is also received. 0 is also received. At this moment, it will slide this window. So basically, it slides the window. Only it will keep on ticking, keep on ticking. It will slides the window only when from the leftmost there are contiguous ticks. Okay. If 0 has been received, 1 has been received, so it will immediately slide this window to this. Right. So if only 1 is received or only 1 and 2 are received, 0 is not received, it will not slide it window. And then it will let's suppose 0 has been lost, then it will retransmit only 0. Right. Yeah, these are not cumulative. Yes. So these are some small scenarios that we have in case of selective repeat also. So maybe if you have went through the videos, then you might know this. So suppose that this is the working of selective repeat. Suppose that data get lost. Suppose this is get lost. Now you have received the acknowledgement for 1 and 2. If you have received the acknowledgement for 1 and 2, then you will just retransmit this 0 only, right? Only 0 will get retransmitted. That's the point. Will window get slide? No. Okay, so window will not get slide, but the moment you will receive the acknowledgement for just 0, then you will slide the whole window, right? And then you will send 3 4 5. Okay, so basically the concept is very simple. Let me write the concept in just maybe 1 or 2 lines. So I will say sender keep on marking the packets, which means let's suppose this is sender window. Okay, this is sender window, and suppose that you have in the center window you have this. Now suppose that 1 and 3 has been these ACK has been received, it will mark them. Will it slide this window? No, currently no. It will slide window only when the contiguous from the left has been received. Okay, slide window left has been received, right? So now suppose that 0 is also received. Now suppose 0 is also received. 0, I mean 0 ACK for 0 is also received. 1 and 3 was already received. Now ACK for 0 is also received. Now it will slide this window to this 2 only, right? This 2 only. Now the next package that it will send is 5 and 6, right? Slide the window till this 2 only. Okay. I hope that is fine to everyone. Now, let's suppose 2 has been lost. Okay. Suppose after that 2 has been lost. After this, suppose 2 has been lost. So it will retransmit 2 only, right? It will retransmit 2 only. Now once 2 has been acknowledgement, after the retransmission, it will slide this window further. Okay. So that's very easy. Now there is one doubt. So present window is 0, 1, 2, and the acknowledgement of 0 from the previous session is delayed, and the received now will the sender slide now. Okay, so previous window is 0, 1, 2. Present window is 0, 1, 2. Let me go to the doubt. And the acknowledgement of 0 from the previous session is delayed. Okay, so you are receiving from the previous session is delayed. Okay, maybe it is possible. So let me just frame this question properly. So suppose you are sending 0, 1, 2, and then this 0, this 1, this 2. Okay, so this is little long question in the sense. So this 0, 1, 2, let's suppose it is received. Now it is sending the ACK for 0, but this ACK for 0 is basically getting delayed too much. Okay, ACK for 0, ACK for 1, and ACK for 2 has been received. For 2 has been received. Now will the sender, now consider this, will the sender slide this window? If 1 and 2 has been received, will the sender slide this window? No, right? Sender will not slide this window. Then what will sender do? Sender will retransmit this 0. Okay, this is retransmission of 0. 0 retransmission. And then suppose that this retransmission ACK has been received. Okay, so this is retransmission, like the sender is retransmitting. Okay, sender is retransmitting 0. Yeah, so in that case, receiver is not expecting 0, right? I mean, receiver will not acknowledge it because receiver is not expecting 0. So receiver is expecting here something else. Say 0, 1, 2 has been received. 0, 1, 2, this has been received. Maybe receiver is expecting for 3, 4, 5, something like this, right? Receiver is expecting for 3, 4, 5. Now you are sending 0. What will receiver do to this 0? Is receiver expecting this 0? No. So receiver will just discard it, right? So receiver will say that, okay, I do not need this 0. So receiver will just discard this. Now this is discard. Okay, so this is a very problematic scenario. The thing is that if receiver is discarding this, then receiver should be notifying somehow that I already have 0. I mean, if receiver discard this, then sender has no way to identify whether receiver has discarded this or retransmission also got failed. So here sender is receiver is expecting 3, 4, 5, and then sender is sending 0. Okay. So I think receiver should discard it. But then at later point in time, this ACK 0 will get received, and then at this point in time, like sender will say that, okay, this has been received, so it will work properly. I mean, at later point in time, this ACK 0 will get received, right? So what is your doubt? Window will not slide. No, window will not slide. I mean, till the moment you do not receive the AC key for 0, it will not slide. Okay, window is this only. It cannot slide. So AC key for 0 must have been received to slide the window. Right. So let's suppose receiver is discarding it, but later point in time, this will be received by the sender. Then the window will slide the whole. So it will be received, and then window will slide, which is 3, 4, 5. Okay. So window will slide only when the contiguous from the left has been received. Now there are different cases. Now suppose that if data get lost, then it will just retransmit the data, very easy. If acknowledgement get lost, then maybe again it may retransmit the data. So if acknowledgement get lost, then okay, this 1, 2 has been transmitted. Just a second, then 0, 1, 2. Okay, acknowledgement for 0 here has been received. So it will just retransmit this 0, right? If acknowledgement got lost, so it will just retransmit this 0. Yeah. Okay. And the third case is if packet get delayed. If packet get delayed, then in this case, I mean, it will send the ACK will also be delayed. So maybe it will take some time, but yeah, to check this 0. But once eventually check this 0, then it will slide the whole window. Right? If ACK is delayed, so okay, first the packet is delayed. If ACK is delayed, then also almost same story. It will wait for some time. Either it will retransmit. Okay, if the ACK is delayed too much, then it will retransmit. If ACK is delayed not that much, then it will just accept it a little later. If data is corrupted, then I can silently discard, or I can send the negative acknowledgement also. Okay, so there is negative acknowledgement that we can send. That is just optional. Now, I hope you have seen the videos. There I have talked about the relationship between the window size and the sequence number. Okay. So why I cannot send the whole thing? Let's suppose these are the packets. Why I cannot send the whole number of packets, so all of this from 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, like that. Because there are multiple packets with the same sequence number. That is not possible. That is not allowed. And why I cannot send this much only? Because receiver should be waiting for complete set of new packets. Right? Okay. So these things we have discussed. Now, efficiency in the sliding window is basically number of packets that you're sending, right? Sliding window, which means go back and or the selective read, both have the same efficiency. Like, I mean, you might be asking then why we have the selective repeat, why we do not have the go back end. I mean, in ideal case, both have the same efficiency. Ideal case in the sense there is no packet loss. But yeah, if there is a packet loss, then go back and suffers a loss, a lot, right? Which means go back and sends too much of the data, the n packets just for the one loss. So that is why this go back n is less efficient in sliding compared to selective repeat if the channel is noisy. If the channel is not noisy, then this is the efficiency that we have, which is same, right? If channel is ideal. Is this okay to everyone? Okay. So if the channel is ideal, then you will be having the same efficiency. But if channel is not ideal, then go back n is obviously less efficient. Right. So now let's try solving some questions. Do we need a break of 5-10 minutes? So I just need, I think, half an hour more, and then we can finish this protocol. Okay. So there are a few questions. Okay. Let me just complete it. Or maybe can you just wait for 5 minutes? Just for 5 minutes. Okay. So I will just come in 5 minutes. Hello. Okay, now I'm audible, right? So what they're saying is that suppose the situation is same as above, and like which means that packet number 22 has been lost, and the sender and receiver uses the selective repeat ARQ. Now, what are the packets that you need to retransmit if 22 has been lost? Then how your window look like? Your window will look like same, and you will you will transmit this 26, 27 extra, but you will retransmit only this 22 if this has been lost, right? So you will retransmit only this 22, and then once the 22 ACK has been received, the whole window will get shifted, right? So you will retransmit only this 22. See the answer? You will retransmit only this 22. I think there is some 25 is some misprinting, but yeah. Okay. So now let's see this question. Can the selective repeat ARQ uses the can this selective repeat use the cumulative ACK? Is there any method that I can use a cumulative ACK in selective repeat? I think if I use a cumulative ACK, it will be clearly a problem, right? Why? Why that will be a problem? So suppose I say that I'm using the cumulative ACK. In this case, since I'm sending the multiple packets, suppose the ACK for this has been arrived. Okay, so can the receiver send the cumulative ACK, which means that if the receiver is receiving all of this, so see, yeah, if the receiver is sending the ACK for this, then if what if these packet has been lost? Or maybe like receiver, I ask the receiver to send the ACK only when that packets the contiguously has been received, which means this received, this received, this received, then only I send the ACK for this. Right? If I send the ACK for this, then it means that 3 packet has been received. Now suppose if I send the ACK for this, then will this be a problem to selective repeat? Then obviously if receiver is also sending the ACK in such a way that all of these 3 are received, then is this a problem to sender? Sender will also think that okay, all of this has been received, then it will tick mark and then it will slide its window, something like this. No, out of packet is also allowed. Why it is not allowed? Like, I mean, you can accept the packet, you can just tick mark, tick mark, tick mark. Whenever there is a contiguous tick mark, then only send the ACK. Right? Whenever there are contiguous tick marks, then only send the ACK. I mean, you accept the packet out of order, but whenever there are contiguous tick marks, you then only send the ACK. You will say that okay, till this part I have received. So suppose I say that okay, till ACK till this part I have received. So let's suppose say ACK 3. It received this ACK 3 and it will slide its window. That's fine. But the problem is that suppose this ACK has been lost. Okay, then sender has no way to identify whether all has been received or only one has been received or 2 has been received, right? Now sender here, if this ACK is lost, sender doesn't know that which has been received. Maybe only 0, only 1, only 2, or maybe all of them has been received. So sender doesn't know. So sender has to retransmit all of them, right? This is retransmission of all of them. Yeah. So this will be just like efficiency will get dropped down. So it will be just like go back in. By the way, can you answer me one question? If the efficiency of go back in and selective repeat is both efficiency just like this is the number of packets that I can send. This is the window size, number of packets that I'm actually sending. If both of them are having the same efficiency, then why to use selective repeat? Why not to use go back in always? If both are having the same efficiency in this formula. So this efficiency formula is just for very optimistic and ideal case when there is no packet loss. But if there is a packet loss, then obviously the those protocols will be less efficient in the sense that you are basically you will be sending more. Okay, I mean you have to do more retransmission and all. So in that case, go back and will be less efficient. But yeah, if channel is ideal, then yes, go back and selective repeat does not matter because you are sending all of the packet WS here. you're receiving here one by one, or maybe you can receive multiple packets. So both are fine. Doesn't matter, right? If the channel is ideal. Yes. Okay. So basically here you cannot you cannot use the cumulative ACK. Reason being is that then it will be just like a go backend. Now, what are the trade-off between go backend and selective repeat? In go backend, the receiver does not keep the state about out of order sequence numbers. It can just discard them and wait for the sender to retransmit them. That is not the case for selective repeat. Anyway, in go backend, you retransmit many of the packets just because of one packet is lost. But in selective repeat, it doesn't. It is not the case, right? Okay. Now let's solve more questions. Let's see this question. Consider the go back and selective repeat protocols. Suppose that this sequence number space is of size k. Okay. So sequence number the number of sequence numbers is basically k. K is the total number of sequence numbers. What is the largest allowable window size for each of these protocols? That will provide the sequence number problem. That will avoid the sequence number problem. So in go back n, here you can have k k minus 1. This could be the maximum window. And in the selective repeat, you can have k by 2, right? And k by 2 for the sender, k by 2 for the receiver. I hope you know why we are having k by 2 and k by 2. Why not just k minus 1 and k minus 1, or maybe k both side? So you know this, right? We have already talked about this in the theory lecture. See here. Here I talked about this, that the relationship between window size and sequence number. Okay. Yeah, duplicate packets will not be get detected if I do this. Now, what is the difference concerning the way acknowledgement are handled in between go back and select repeat? So go back and uses the cumulative, it uses the single acknowledgement, like normal acknowledgement. Which of these two acknowledgement method is used by TCP? Okay, TCP will. Okay, this is individual packet. TCP we will see later. So I think that is fine. Yeah. So now let's move to this question. What they're saying, suppose that suppose you attach a network monitor to observe the sequence of packets that travel over a link from node A to node B. So from node A to node B, you are sending something, and you observe the packets that you are sending. Your job is to deduce what protocol, if any, could have been generated these observed sequence, which means that they will give you that, okay, you are sending packet number 0, then waiting for some time, okay, waiting for some time, and then you are sending packet number 0. Okay, this is the traffic that you are generating in this question. This is the traffic that you are generating from A to B, which means one scenario is this, like you are sending 0, and then you are waiting for some time, then you are again sending this 0, you are waiting for some time, you are again sending 0. So they are saying that which protocol could have led to this situation? What do you think? Could stop and wait have generated the diagram? Could go back and could selective repeat? If go back and selective repeat, B or C, can generate this particular sequence, okay, then what is the strongest conclusion that you can infer about the value frame? Then what should be the window size? That's what they're asking. So let me just repeat the question. They're saying that from A to B, they have observed that the sequence of packets that they are sending is like this: 0, and then they're waiting for some time, then they are again sending 0, then they're waiting for some time. Then what kind of protocol they might have used? Maybe stop and wait, right? Because maybe they are sending 0, maybe 0 is getting lost, and then again they need to send 0, maybe again they need to send 0. Maybe stop and wait can generate this, right? This diagram can go back and generate this. Yes, if window size is just 1, then go back and selective repeat are same as just stop and wait, right? So if window size just 1, then go back and can also generate this, and selective repeat can also generate this. So let's see the answer. So this is answer for diagram 0. Okay, diagram 0 is this one. This is the diagram 0. Here all 3 zeros are the same packet that you don't know. Okay, I mean, you don't know whether they are same packet or different packet. You just observe the sequence number, okay, which is 0. Now you need to check whether like with what protocol they might be, that might be the case. So that might be the case with stop and wait, right? Where you are sending 0, maybe this has been lost, and then you are sending again, maybe this has been lost, something like this, right? And if you are saying that these are the new packets, then generally we have the sequence number 1. I mean, we have 2 sequence number for any protocol to work. Okay, so mostly it is the old packet only. Yeah, mostly it is an old packet only. It cannot be a new packet. If it is a new packet, then there is no protocol that we have for this. Yes. So from A to C, that can be stop and wait. SW means stop and wait. Go back and or SR. A to C means, okay, these are the A to C, that which protocol you might be using. D is asking that if you are using go back and or selective repeat, then what should be your window size? So you can have any of this. So it is saying you can have any of this. And then D is saying your window size must be greater than or equal to 1. Explanation means and must be at least 1 in any go back and select repeat. In D0, we only see 1 frame being sent. This gives us no upper bound on it. So they are saying that window size need not to be just 1. It can be greater than or equal to 1. So after 0, you are waiting. Yeah. So if I talk about that, this particular diagram could have been generated by stop and the go back and or select and repeat, then can you comment about the window size? Should it be exactly equal to 1 or can be greater than equal to 1? I mean, it can be 2 also. Tell me. It should be greater than equal to 1. Reason being is that like it need not to be exactly equal to 1. Suppose it is 2. Then yes, I agree that after 0, you must immediately send the 1, right? Suppose it is 2, then in go back and or select repeat, you must immediately send 2. You immediately send 2 packets, not just 1 packet, right? But what if this 1 is not available from upper layer, not ready data? I mean, you don't even have that data. What if that is the case, right? So basically, if you are generating the 0, 0, 0, if you observe that, okay, 0, 0, 0 was sent, 0 and then 0, then 0, could we go back and also, maybe with any window size? What if the other frames are not even ready? So the window size could be greater than or equal to 1, right? Now, the next question is saying you are sending 0, 1, 2 without any waiting, right? So this was the wait, but now without any waiting, you are sending 0, 1, 2. So which means from A to B, you are sending 0, 1, 2 immediately. 0, 1, 2. Can it be stop and wait? No, right? So stop and wait, no. Can it be go back and? Yes. Can it be selective repeat? Yes. If it is go back and or selective repeat, then what can you say about the window size? Should be at least 3, right? Should be at least 3. Should it be exactly equal to 3? May not be, right? It could be 4 also. What if the other data is not available? So this window size should be greater than or equal to 3. Let's just check. So cannot be stop and wait, right? Now window size should be greater than or equal to 2 or 3. This is 0, 1, 2, right? Yeah, it should be 3 only, I think. Can we go back and or stop and wait? Go back and or selective repeat. Thus, there must be an ideal time between sending 0 and 1. A similar argument applies to sequence number 0. SN means sequence number. Okay, SN means sequence number. So they are saying there must be some wait if it is stop and wait. N is greater than or equal to 2 because the ACK for packet 0 with received number, I think maybe RN ACK number equal to 1 could be received during the transmission of packet 1. Packet 2 can be sent as soon as transmission of packet 1 completes. Okay, so they are saying that it could be just 2 also. Yeah. So see, why it could be just 2 also? Should it be 3, at least 3, or it could be 2? That's the question, right? Which means from A to B, if you are sending something, and if there are 3 packets, let's suppose 0, 1, 2. If there are 3 packets that you observe that you sent 0, and then from A to B, you don't know what is happening from B to A. Okay, you don't know. I mean, that's not what you are monitoring. So this is 1, this is 2. You observe that, okay, immediately after 0, you are sending 1, immediately after 1, you are sending 2. Then what should be the window size? Can it be 2? Can it be 2? That's my question. No, available sequence number you don't know. I mean, 0, 1, 2, 5, it could be anything. There is nothing. Maybe it is 100 or something. Okay, available sequence number is not a concept here. My question is that even immediately after 0, you are sending 1. Immediately after you are sending 2. Then what should be the window size? See, let's ask, can it be 1? Can it be 1? If immediately after 0, you are sending 1, you just finished transmitting 0, then can it be, can you send 1? If the window size is 1, no, you will wait for the acknowledgement, right? If window size is 1, then there must be after 0, then you once finish this, there must be some wait time. You will wait for acknowledgement. If window size is 1, right? Then only you will send 1. If window size is just 1, is this okay to everyone? With window size, it's just 1. Now, let me know if that is okay. Then we will move to the next case. Okay. So now, suppose that your window size is 2. Now, in case of window size is 2, you will send 0. Immediately after that, you will send 1. That is perfect. Now, will you wait for some time to get the ACK for 0? And then you send 2 and 3. Should there be a gap here if window size is 2? Should there be a gap? That's my question. Tell me. You send 2 packets and then you wait. May not be, right? Why? Why may not be? Because you just finished transmitting 0, and the moment you are sending 1, right? The moment you are sending 1, you started sending 1. What if 0 has been reached and the ACK is also traveling in the opposite direction? ACK for 0 is traveling in the opposite direction. You started sending 1, which means at this point in time only you started sending 1, and then ACK for 0 is approaching to B. Then the moment, let's suppose you finish sending 1, I immediately got the ACK for 0, and then I immediately send packet number 2, right? So what is happening here is that you have sent 0, and now this has been received 0, that is okay. Now it will send the ACK for 0, right? ACK 0. And then, I mean, let's suppose you took some time to send this 0, and then it has received. So now you are sending 1, right? The moment you finish transmitting this 1, the moment you finish transmitting this 1, at the same time you got the ACK for 0, then you will immediately transmit the 2. You will immediately transmit the 2, right? So you can send 0, and then it will take some time to reach. Meanwhile, right, it will take some time to reach, and then the acknowledgement will come. Meanwhile, you're transmitting the packet number 1. You are transmitting the packet number 1. This is the packet number 1. You have observed that, okay, you have just transmitted the packet number 1. Immediately after you finish transmitting the packet number 0, you started transmitting at the packet number 1. So let's take some timelines. Let's suppose that at t equal to 0, you started the transmission of packet number 0. At t equal to 5, you finish the transmission of packet number 0. And at t equal to 5 only, you started the transmission for packet number 1. This is with respect to A. Now, what is happening at side B? Okay. So, okay, let's suppose this is t equal to 10. At t equal to 10, you finish the transmission of 1. This is what it is happening, right? Now, yeah. So let's suppose that your propagation time is not much, which means let's suppose this like while this zero is transmitting, let me just tell you, let's suppose that at t equal to in between here at b, okay, at b, in between here at let's suppose t equal to 7.5, this zero has been received. Zero has been received at b. Now it will immediately start the transmission of ACK. And let's suppose at A, this is from B to A, at A, at t equal to 10, at t equal to 10, right? The ACK has been received. ACK has been received. Right? So in this case, the moment you finish transmission of one, at that time, you will get the ACK also. So, okay, you are asking for the relationship between TP and TT. So see here, yeah. So basically, you will say that this whole need to get transmitted. This whole need to get transmitted, right? So don't worry about the should get propagated. Don't worry about the transmission time. So it will take the TP time to reach here. Just think about this. This zero will take the TP time only. TP time to reach here. Okay. You just think about the last bit. If you are confused, just think about the last bit. It will take TP time to reach here. Acknowledgement will take again how much time plus transmission time of acknowledgement. Okay, generally it is 0 plus TP time, TP time to reach here basically. So let me just make it 0. So basically you will take 2 TP time to reach to get this acknowledgement, right? Now in this meanwhile like when 0 is traveling and then all, if that much time you're taking for the transmission of the first packet, which is TT, right? Then if that much time you're taking, then by the time you finish transmitting, you will also receive the ACK. So you will immediately send 2. So yes, that can happen without any wait. That can happen. You do not need to wait. Even if your window size is 2, you send 0, 1, immediately you can send 2, even if your window size is 2. Right? That's very good question. So basically, that's what they are saying. The window size should be greater than or equal to 2. Now let's see the last one, this one. So they are saying that this one could have been 210. This one could have been the case of which protocol? So 210 and 210. So case is asking, in case of packet loss, we cannot send. Yeah, like that's not what they have asked. They have asked that this is what they have observed. This is the sequence that they have observed. Now you need to reduce the protocol that you are using. Okay. So yes, in case of packet loss or these kind of things, then there must be waiting in between, right? But that's not the case here. Like this is what you have observed. Now you need to guess about the protocol that you are using. If you are using selective repeat or go back in, then what should be the window size? At least. Okay. Okay. So if 210, let's suppose 210, you are sending something like this without any delay, right? See, without any delay, you are sending 210. Then can it be stop and wait? I don't think it can be stop and wait. You are sending packet number 2. Okay, the sequence number does not matter here. I mean, you can start from 0, you can start from any sequence number. It should be just different sequence numbers. Okay. I mean, you can have 1, 0, 2, anything. Okay, doesn't matter. So you are sending this 2, then you are sending 1. Immediately after that, you are sending 1. Immediately after that, you are sending 0. Then obviously, it cannot be stop and wait. It has to be selective repeat or go back in. But now the interesting thing is that what should be the window size of this? If you are sending 3 packets, लगातार 210, and then immediately you are sending 210, next sequence of packets, what should be the window size? Window size cannot be 4, obviously, because window size is 4 means that you are sending them simultaneously, which is not possible. Okay, so basically window size could be 3, I mean at most, but at least what should be? Can it be just 1? It cannot be 1. Can it be just 2? Can it be just 2? Can I just send 2 and 1, 1 and 2, or maybe 2 packets? And by the time I finishing these 2 packets, let's suppose the ACK for 2 has been received, then I send this 0 also. By the time I finish sending this 0, right, then the ACK for this has been received. Sorry, I will send 2. I mean, that's how I'm marking it. So basically I'm sending 2, 1, let's suppose. By the time this, like I'm transmitting this 1, okay, I just finished transmitting this 1, I received the ACK for 2, so that's why I can start transmission for 0. By the time I finish the transmission for 0, I get the acknowledgement for 1. So I will shift my window, right? So I think with 2 should work. Window size 2 should work here. Okay, they are saying at least 3 you need. I don't think at least 3 we need. Can we go back and selective repeat? Because all reverse packets could be delayed so long that the A retransmit all the 3 packets. Okay, this is a retransmission that they are saying. Okay, these packets are retransmission. Is this? Okay, let's say that what if these packets are retransmission? It means that it cannot be 2 in that case, right? I mean, it could be 2 if this is the new packets. If these are the new packets, then definitely it could be 2, right? Because the moment you finish the transmission of 1, you may get the acknowledgement for 2. Then you will slide your window. See, in your window it is like this, right? So suppose your window size is 2. Now you will send 2 and 1, right? So you are sending 2 and 1, which means you will send 2 and then you will send 1. Now the moment you finish transmission of this 1, you can get the acknowledgement for 2, right? And then you will slide its window. So you will say that, okay, my window is now this. Now in this case, just after finishing this transmission, you got the acknowledgement. So you will slide this window and then you will immediately send this 0. Then you will get the, let's suppose just after finishing the transmission of this 0, you get the ACK. Okay, you get the ACK for 1. So you will immediately shift its window to something like this. Right? Then it means you will send 2. So you can send 210, 210 like that, right? Even if your window size is 2, and these are the new packets here. But what if this 210 is the old packets? If this is 210, I'm sending 210. Now I'm again sending 210 without any delay, but these are the old packets only. So what should be the window size? Can it be 2? See, if it is 2, I'm sending this, then I have to get the acknowledgement for this 2. But since I cannot get the acknowledgement for the 2 because I'm actually retransmitting, it is given to me. Okay, it is given that these are the old packets. Suppose it is given to me that these are the old packets. Then it cannot be 2, because if it is 2, then I cannot retransmit, obviously, if I'm getting the acknowledgement for this. Because see, for the 2, what I need to do, I have to get the acknowledgement for 2. Then only I can slide the window, right? But they are saying that you cannot get the acknowledgement for 2 because you are retransmitting. So that is why the window size cannot be 2. Can it be 3? Let's just check. Can it be 3? With 3, what you will do? You will send 210. I mean 2 and then 1, then 0. And the moment you finish the transmission for, let's suppose the moment you finish the transmission for this 0, let me have this kind of diagram. You transmit this 2, you transmit this 1, you transmit this 0. This is 2, 1, 0. Now 2 might have reached till the end, and or maybe the timer got expired, okay, and or maybe data got lost and the timer got expired. So you will say that, okay, the timer got expired, so that's why maybe the timer is expiring just here. So you have to retransmit this 2 again, right? Because the timer got expired. So you have to retransmit this 2 because the timer got expired. Similarly, maybe the timer for 1 can get expired here, timer for 0 can get expired here, right? So yes, this is possible if these are the old packets. The window size 2 is not possible. Window size have to be greater than or equal to 3 if these are the old packets. If these are the new packets, right? If these are the new packets, then window size can be greater than or equal to 2 also. Okay. I hope you understood. Let me know if there is any doubt. See, you are just, if these are the new packets, you are sending 210, and for the new packet, you have to slide your window. So that's why you have to acknowledge it and then immediately slide the window. The moment you are receiving the acknowledgement, you finish the transmission for 1, you are receiving the acknowledgement for 2. That's why you can start the transmission for 0. Okay. So these are 1-2 small questions that you may try it, okay, as an homework. Let me just write as an homework, you can try if you want. Or should I do it now? Maybe you can try as an homework. This E might be little interesting. Okay, just try doing it. Definitely try doing it. Don't skip it. Okay, don't skip this. So yeah, so I think there are few questions that you can try as an homework. Like, I mean, there are easy questions only. In GATE, they will ask just easy questions, just like these kind of questions, or maybe these, the minimum, maximum, what should be the available sequence number and all. So in GATE, there will be just easy questions. We have covered everything. And like I have seen the GATE questions, these are not tough questions. Even we have covered some little tricky questions. So the ultimate idea is that, I mean, in the any of this protocol, that you have like given the bandwidth and RTT, you can immediately find out that how many packets you can fill with. And if you want to know that how many this is in the bytes, if you want to know how many packets you can fill, then you can divide by the L, or maybe you can directly do 1 plus 2a, or maybe just 2a, right? So it depends whether it is 1 plus 2a, 2a, it depends on RTT. Okay, let me just go to the next page. Maybe let me show you what do I mean. See, this is bandwidth into RTT. Now this is number of bytes we can send, right? Number of bytes. Now if RTT, let's take a case 1, if RTT is 2 TP, a case 2, if RTT is 2 TP plus TT. In this case, if you want to convert into number of packets, then it will be bandwidth into 2 TP upon length, bandwidth into 2 TP plus TT upon length, right? So it will be 2A only, I mean 2 TP upon TT, you can do it, right? And then in this case, it will be this is TT, then it will be 2A plus 1, right? It depends that what is the RTT you are taking. Okay. So based on that, your efficiency will be 1 upon 2A, or maybe 1 upon 2A plus 1. Cool. So that's the only idea that we can use. And now you know working of these protocols, right? Now you can solve these kind of questions. Okay, great. So tomorrow we will be starting some new topic. Okay. Yeah. Thank you. Thank you so much. Let's meet tomorrow.